So I shall try to add some more thing on transfer on the network functions. Some remaining part I will leave for you to go through because it is that way easy, and then we shall move for the last module. So network function is always a ratio of some voltage and some current. Ratio of some voltage and some current. If both are at the same port, it happens to be a driving point function. If both are at different ports, it becomes a transfer function. And when I say ratio, the idea should be very much clear is that so transfer function provides you the characteristics of the system. It provides you a systematic, usually we go for transfer function, usually. So it provides us a systematic description of the relationship between output and input. Means, in a way, it describes it happens to be a system property. Transfer function happens to be a system property, and it is the ratio. When I usually voltage gain transfer function, the G21S is predominantly used, and that provides us the nature of the system. Basically, I again repeat what G21S is a ratio. G21S is a ratio. Ratio of what? Ratio of what is again a question. Ratio of the output voltage V2T upon input voltage V in T if e raised to st is applied. When we apply the network is to consist of linear elements. If ever diode comes in network, then all these theories fail. These theories are applicable only for linear networks. So the network may contain resistor, inductor, capacitor and dependent source. Network itself cannot contain an independent source because it is non-linear. Non-linear is it has some fixed value. It does not have any relationship with input output. So for such a network, it is very much clear that when we apply the network elements are R, L and C, means all these elements exhibit a linear relationship between voltage and current, either directly or in differential manner. When we talk of differential manner, e raised to st is such a kind of input signal or is such a signal for which its differential and integral are nothing but its scalings. I am using these so many times that at least maybe somebody may understand everything, or by Bobel's logic everybody will start at saying that for e raised to st means what? Differential means scaling. E raised to st means integral means scaling. So d by dt of e raised to st is s into e raised to st, and integral 0 to t e raised to st dt is 1 upon s into e raised to st. That is what we can say, if ft is e raised to st, then f dash t is s into ft, and integral of ft is ft upon s. And therefore, we get a concept of impedance, and the differential equation reduces to a linear equation. And because of this, voltage and current, between any two points or current through any path is always something into e raised to st. That something may be one dimensional, that something may be two dimensional. E raised to s is a, we are using complex terminology just to get the idea. The complex number system in the form of x plus jy is the introduction of j is just used to simplify two-dimensional geometry and their interrelationships. Otherwise, there is nothing like imaginary and real. So j square equal to minus 1 e raised to j theta is cos theta plus j sin theta. When these two things we understand very clearly, we do not get any problem. So e raised to st, what e raised to st is? E raised to st is a point which is moving in a 2D plane with respect to time in a particular manner. If s is equal to, if s is sigma plus j omega, we say if sigma is 0, then e raised to st becomes either e raised to j omega t, omega and positive or negative. In that case, that becomes movement on the unit circle. If omega is 0 and it is only e raised to sigma t, then what happens is that it is a movement of point in a 2D plane. It is a movement of, I again repeat, t is not this. E raised to st itself is two-dimensional. E raised to st itself is two-dimensional. And what is t? When I am moving it, at what time it is occupying which space, there I am putting t. So if omega is 0, what will happen? If omega is 0, then at t equal to 0, it will be 1. And if sigma is positive, it will move like this. Right? And if sigma is negative, from 1 it will become asymptotically towards. Again, this is most important. E raised to st is mapped as a point in a two-dimensional plane. E raised to st is mapped as a point in two-dimensional plane. If sigma is 0, then at t equal to 0, e raised to st is here. And then if omega is positive, it rotates on the unit circle like this, continuously, depending on omega, higher angular speed, lower omega, lower angular speed. If sigma and omega both are 0, it is dead constant at 1. E raised to 0 t, 1. If omega is negative, it rotates like this. If omega is 0 and sigma is positive, then at t equal to 0 it is like this. When t advances, it moves on this side. If sigma is 0 and omega is negative, sorry, if omega is 0 and sigma is negative, then at t equal to 0 it is here and comes on this side. Asymptotically. Asymptotically means in time capital T, if it moves from 1 to half, then in next capital T it moves from half to 1/4. 1/4 to 1, it never reaches 0. It never reaches 0, it never reaches infinity. And then multiplying e raised to st by a function of s means what? Multiplying e raised to st means multiplying a point in 2D plane by a function of s means if a function of s, say s plus 2, s is sigma plus, means again it is s plus 2 itself is one two-dimensional quantity. So because of this, when we multiply one point by the other, it may, if the multiply is real, is real, what will happen? If the multiply is real, then the original point will move on the axis connecting that point and 0. If that multiply is more than unity, it will go away. If multiply is less than unity, it will come back. If the multiply is negative, it will go on the other side of the axis. If multiply is only imaginary, then it will rotate either on this side or on this side. But if multiplier is real plus imaginary, then it will move away or towards as well as rotate. So ultimately, multiplying e raised to st by some constant means you have liberty to shift it anywhere from the current position. So any position in 2D plane can be considered to be any other position with some multiplier. So that way one can very easily say that if e raised to st is the input signal, then output signal or voltage at any point or current through any arm will always be something into e raised to st. And then when it is something into, when input is e raised to st, voltage and current at every point or at any arm is something into e raised to st, then we can take the ratio of that upon input, something into e raised to st upon e raised to st, that gets cancelled out, and that something becomes the transfer function. That something becomes the transfer function. This. If I apply e raised to st here, then what I get here is something into e raised to st, and that something is 1 upon s plus 1. That something is 1 upon s plus 1. So that provides us a systematic idea about the nature of or the gain the system, or that rather G21S, which is the transfer function of output voltage upon input voltage, describes the system in all. It is a property of the system, it describes the system completely. It is ratio of output upon input voltage V2T upon V in T if V or V1T if V1T is e raised to st. Or the alternative way, any V in T, V1T you can have. If you find its Laplace transform, it will be V1S. You will be getting some V2T, that its Laplace transform is V2S. And if you take ratio of V2S upon V1S, that will also be G21S. Then what G21S indicates? G21S is the ratio of output Laplace transform or input Laplace transform. If I ensure that input Laplace transform is 1, in that case the gain would be, the G21S would be output itself. Then if I take inverse Laplace transform of G21S, that is G21T, this can be the output voltage time signal V2T if my V1T is inverse Laplace transform of unity. Inverse Laplace transform of unity is impulse function. So the output voltage signal V2T is the inverse Laplace transform of G21T when input applied is impulse. It is the characteristic response of the system. Impulse is said to be all inclusive input. Impulse is all inclusive input, and we get the output. So if we apply impulse here, the output will be like this, because inverse Laplace transform e raised to s plus 1t is e raised to minus t. Then this is one. Then the second we discussed the L and C. What it will give? It is L and C. What we get? 1 upon s plus 1 upon s multiplying by s 1 upon s square plus 1, whose inverse Laplace transform is sin t. So it is sustained oscillations. Suppose somehow, I say somehow, you can't prepare such system. It is a task to you. That suppose there is a system like this, which we can't have so easily. I right now don't know. Such that G21S is 1 upon s minus 1. G21S is 1 upon s minus 1. What will happen? What would be G21T? It would be e raised to, correct? E raised to t. Now you see the importance. When it will occur? If I apply input as impulse. So I am applying, impulse is not infinite input. Impulse is input of infinite magnitude but lasting for 0 time. So its area under the curve is 1. So suppose if I slap you today, what you will do? A stable system, you will start crying loudly, and after some time you will stop crying. Or sometimes maybe the children do that. If I slap now, they start crying, and the crying goes on increasing. So the same is happening here. An impulse applied. An impulse applied to the system. Impulse has come, it has gone. See the output. Output is ever increasing. It is an indicator of unstable system. Input applied, input has come and gone. Like this. Stable system. And input has come and gone. But oscillator system. So three types. Poles in the left half of S plane, stable system. Poles in the right half of S plane, unstable system. And poles neither in the left half nor in the right half, but on the vertical axis, imaginary axis. In that case, oscillator system. Here, when I give the impulse, impact goes down. So here I give the impulse, impact continues to rise. Here I give the impulse, impact neither grows nor dies. Is it clear now? So it is the pole's position is describing us the type of the system. The position of the poles. So when you are having a big polynomial, you can find its partial fractions. The fractions may be real or imagine complex. Once complex roots are allowed, any polynomial you can decompose. When complex roots are allowed, any polynomial you can decompose. You can decompose s square minus 1 is s plus 1, s minus 1. But you can't decompose s square plus 1. If only real roots are to be considered. But the moment at which imaginary and complex roots are allowed, s square plus 1 is decomposed as s plus z, s minus z. So with complex roots allowed, you can get any decomposition. And based looking at the location of poles, you can conclude whether the system is stable, unstable or marginally stable. Right? Then there is a Ruth criteria for stability of the system, which I leave it up to you. It just means that Ruth criteria allows us to identify the location of poles without actually going for finding roots of a polynomial is not impossible task, but is tedious task. Are you getting me? Finding out roots of a polynomial is a tedious task. So without going for that direct finding, the Ruth criteria provides us, just by looking at the coefficients, some kind of what we can say it's number jugglery by some fixed standard method of writing down the coefficient in a given order, and there is a simple method to be followed that will provide you whether the system is stable or unstable. That I am leaving up to you. Right? So what I see at the end is the chapter of, and one more thing, if only passive components are there, it is R, L and C, system will never be unstable. System will never be unstable. This is because the values which the passive components can take, that is R, L and C, are always positive. R, L. Now, so I can draw the, what I said that this you can't do. G2 and S equal to S, 1 upon S minus 1 you can't do. G2 and S equal to 1 upon S minus 1 you can't do. But then somebody will say, no, why? I will do it. Somebody says, why I can't do it? I will do it. What will happen now? What will happen? 1 means 1 upon S. So 1 upon S upon 1 upon S minus 1. Right? Multiplied by S, it is 1 upon S minus. Sorry, 1 upon minus 1 upon S minus 1. Minus. We are interested in pole. So we are interested in pole. So we are able to have it. What is the problem now? Why it can't be realized? Because we can't get microresistance. unstable system, that is the systems which will have roots on the right hand side of the S plane, cannot be constructed, because if ever these are to be constructed, we will require the components with, or we can say like this. What will be there? S upon S minus 1. If ever we are to obtain the transfer functions with roots on right hand side of S plane, we need to have the components having negative values, and we can't get them. So by using passive components only, we can't construct the unstable system. The question of unstable system comes only if we are having some active elements. Only if we are having some active elements. That is, we have some dependent sources, and the dependency of the source is such that it is self-increasing. Means it is dependent on something. When that increases, that something also increases. So it's a looping circle. It depends, A depends on B, A depends on B, right? A equal to KB. This dependence is such that in turn B also depends on A. B also depends on A. So B equal to A equal to K1B, B equal to K2A, A equal to K1B, B equal to K2A. If it is so, then where it can contain itself? If A equal to K1B and B equal to K2A. So at what point it will contain? At what point it will contain? A equal to K1 K2A. A equal to K1 K2A. So what is going to happen? If K1 K2 is not 1, if K1 K2 is more than 1, what will happen? If K1 K2 is more than 1, in that case it will be an inconsistent equation. Inconsistent equation, and in that case it will go unstable. Means we can give a very simple example of usually we don't have, just as a fun I am giving. If I eat more, I grow more. Right? If I eat more, I grow more. And if I grow more, I need to eat more. Are you getting me? If I eat more, I grow more. And when I grow more, I need to eat more. So what will happen? I am small. I will eat. So eating is a cause, growing is an effect. Okay? But so the relationship is eating is a cause, growing is an effect. Is one relationship. And also as I grow more, I need to eat more. So in that relationship, growing is a cause and eating is the effect. Right? So I am small, I eat, I grow. So I eat more, I grow more. And it becomes unending. It becomes unending. It's an unstable system. It's an unstable system. Right? So when we are having dependent sources, and the proportionality of dependent sources is such that it is means once connected in the system, it is increasing. Then when we, that is if such thing is there, even if you connect some small thing, it starts escalating. the dependency relationship in overall system is such that when it is right now it is having some value, such dependent sources may give rise to what we can say unstable systems. It is not that dependent source always give rise to unstable system, because if we have normal logic, yes, when I eat more I grow more, but when I grow more, if that doesn't create a need to eat more, in that case it will be a good relationship. So dependent means all passive systems are stable. All passive systems are stable. That doesn't mean that all active systems are unstable. We can't get an unstable passive system. But active system may be stable or it may go unstable also. What we mean by instability? Instability means we will be getting ever increasing output. But from where it will be generated? It needs dependent sources. From where I get dependent sources? Dependent sources I get from some transistors and op-amp based circuitries. So dependent sources is that I have a dependent source is equal to 2Vx. A dependent source is 2Vx means what? It will generate double the voltage than whatever is there at between Vx. I draw Vx, right? Means what? It generates voltage which is double the Vx is somewhere, some voltage in the circuit, somewhere here. So whatever is this Vx, it generates double than this. A system going unstable means if everything works as shown, then it will continue to generate more and more. But this has not fallen from a heaven. The dependent source has not fallen from heaven. Not fallen from heaven means dependent source are you thinking of a ideal dependent source? So mean to say not fallen from heaven means that ideal dependent source should generate 2Vx, that's all. What is Vx? Double than that. But practical dependent source cannot generate that. Practical dependent source cannot generate that. So what it will be able to do? Practical dependent source? Practical dependent source is equal to 2Vx subject to a maximum limit. Subject, because this is constructed from some op-amp based circuitry, transistor based circuitry, which is having its maximum supply value. So the output generated by that arrangement cannot grow more than the supply value. So practical dependent sources cannot generate. This is 2Vx subject to max 50 volts. 2Vx 50 volt max is a practical dependent source. And the moment at which it reaches that state, it no longer remains a dependent source, right? Because Vx may be 30, but it is 50. So the very concept of our linear network fails and system gets non-linear and up to some limiting state. So unstable output, unstable system, unbounded output is never. So you should not be afraid that in practice it may happen so, right? But in actual one, you should not be afraid. Suppose no, then the question asked. The students were asked to. There was an task. We did not assign any task, but in a class the task was assigned. So you demonstrate the working of an unstable system. And the students said did not do anything. And in the oral teacher asked, Why did not generate? Why did not demonstrate that? Sir, I was afraid that what is the unstable system characteristic? For bounded input, it generates unbounded output. So he said that if I construct the experiment as discussed, if I start the system, then it will generate infinite voltage and I will get shock. Because of this fear, I did not go for demonstrating this unstable system. What it means? No system which you prepare will give rise to infinite output voltage. It will stop to be a linear system and will reach a maximum value. Output will reach a maximum value, not beyond that. So unstable systems end up by becoming non-linear and getting some maximum value. They never generate anything unbounded. So that idea should be very much clear, that unstable in the sense, cyclically if we are having the dependency wherein we are having its 2Vx like that. If that works fine, if that is maintained, in that case theoretically output is unbounded. Output is unbounded means, but what is the interpretation? That the circuit arrangement doesn't put any bound on the output. Therefore, the bound is because of the constructional limitations of these active components. Unstable system, output is unbounded means when you theoretically look at the circuit and its behavior, no finite bounds are put on what the output should be. What the output should be. But what the output can be depends upon the constructional bounds in the preparation of the or design of the dependent source. Design of the dependent source is always limited to a maximum value, and when that maximum cap is there, at that point the system stops. So you remove the concept of unstable system giving rise to some disastrous situation. It is not like that. So network function provides us a ratio of output upon input majoritarily, and depending upon that ratio, by looking at that ratio, we understand something. And when we are going for the next chapter, that is the filters, it is same thing again which we are studying. So now I will have an introductory discussion of filters today, and tomorrow we will proceed to a large extent. Pause. Not stop at pause so that I will take attendance. So now let us go for discussion of filters. That is last module. When we are discussing about this module of or the concept of filters, at initial stage we stick to one assumption that the input which we are considering is sinusoidal in nature. We are discussing the effect of the circuit if a sinusoidal input is applied to it, say cos omega t. If cos omega t is the input applied, if cos omega t is the input applied, what the output would be, is that what we are discussing. So we take a simple circuit. What is the output now? If input is cos omega t, what is the output? Half cos omega t, right? Means if omega is phi, if input is cos phi t, output is half cos phi t. If omega is 10, cos 10 t, half cos 10 t. So, in this circuit we find that the output is always half times the input. Half times the input. Rather than that, if I take this input, this circuit, and input is cos omega t, what is the output? What is the output? Again we start with simple one and then we step up to difficult things. What is the output? If input is cos omega t, what is the output? It is cos we get a differential equation, and when we get a differential equation, we get two terms, that is transient and steady state. I think we have solved that. Okay, just as a practice you solve it again. This we get when we have solved that time we are having this one. That time we had a cos omega t generator and we were putting it in the system at t equal to 0. In that case transient and steady state occurs. But if we presume that this has taken place much before, from infinite time cos omega t is here, in that case it is very easy to get the output. What is that then? If cos omega t is here, in such case it means for a circuit consisting of R, L and C, and if it is presumed that the input which has been there in place from substantial amount of time, in such situation voltage and current at all points are sinusoidal only. If I have R, L and C in the system, I am applying a sinusoidal input of some frequency, then if I presume that it has been a situation from quite long back, in that case it can be safely assumed that voltage and current everywhere is of same frequency, different amplitudes and different phases. Or in other words, it can be expressed as A cos omega t plus B cos omega t, B sin omega t, where A and B are constitutive founder. Are you getting me? In an RLC circuit, when I apply input as cos omega t, then voltage everywhere and current from every R can always be expressed as something sin cos t plus something sin t, or something cos omega t plus phi. Both ways you can have. So A sin omega t plus B cos omega t is the way with which we are talking about. So you can assume it to be A cos omega t plus B sin omega t and find out what is the answer.
Sin minus cos of 1.
What is the answer?
Sin minus cos of 1.
Cos omega t by S.
Sin minus cos by 2.
Ooh. This disastrous. Why disastrous? Because S is not to be used at all now. When S is to be used? When input is of the type e raised to st. We are going for a wider class. In cos omega t, it is not to be used at all. Input is cos omega t, output has to be A cos omega t plus B sin omega t.
half
B
B.
also half, right? So half, only half, that's all. Frequency increases, amplitude will reduce, and when frequency is less, amplitude is more. And for high pass filter, it is exactly reverse thing. So filters are offering the gain which is frequency selective. Filters are those networks which offer the gain which is frequency selective. Okay. We'll continue tomorrow at scheduled time. I think tomorrow we shall